Welcome to our online webinar, online panel session about a very fascinating topic today. First of all, my name is Henry. I'm working for the Austrian Research and Promotion Agency. And for me, I'd like as well introduce my colleague from the Vienna Business Agency, Sophie.
Thanks very much, Henry.
Yeah,
Go ahead.
It's a pleasure for us having you in this fascinating webinar about how to access quantum technologies into your business. And for this, we have two speakers who are going to share their insights about potential use cases, about their researches, about how to use quantum technologies. On the one side, we have Tinka Milovancev from the Austrian Institute of Technology, and then we have Manuel Pangl from the Erste Digital. Thank you very much for sharing with us your insights. But first of all, Sophie and myself, we would like to share actually why our agencies are doing this. So I'd like to hand over to you, Sophie, for
Thank you very much.
first step.
Thank you, Henry, for the first few words. Yes, I'm really excited to be here with you, Tinka and Manuel and Henry, of course. Almost afternoon, late morning. Yes, the Vienna Business Agency, obviously, as most people have realized, that quantum technologies are going to be one of the key research objectives, one of the key technologies to actually transform Vienna and Austria. We really were leading when it comes to research. The Nobel was one of the climaxes of that very fact. But I was very interested in how to actually apply said research. Obviously, we, as the Vienna Business Agency, are particularly interested in how to stimulate economic growth, how to translate that fascinating research into actual applications. So this year, in the year of quantum, nonetheless, we will put a focus on quantum technologies. We're planning on, when I say we, I mean particularly me, but also my colleague Dominic Kahner from the ME23, and we're in collaboration with FFG, because we're quite aware that we can't really tackle that topic all by ourselves, but we'll write a report on the Vienna ecosystem in quantum technologies, which is supposed to come out later this year. We're going to have a co-creation lab actually next week coming up to kind of feel out what the ecosystem needs to grow and flourish, and tackle that topic. And then there's also going to be an event on the 2nd and 3rd of October this year at the Wiener Rathaus in collaboration with the VCQ. You can already find that in the event calendar of Quanta. So there's going to be a few little pointed action points that we're going to tackle this year to really get into quantum technologies and support it best we can. Yeah, back to you, Henry. Really looking forward what our presenters will have to say about all of that.
Thank you very much, Sophie, for your insight about your activities at Vienna Business Agency. And I'd like to give you a short introduction to my side as well. I'm working with the FFG, the Austrian Research and Promotion Agency. And since actually now, I think 2 months, I'm officially in the position of the quantum services at FFG. So this is a really new position where we would like to get a deeper dive into the quantum ecosystem as public agency, to get as well an understanding what are your needs, how we can support you with further fundings or more individual and hands-on fundings. And this position is about community building to strengthen this actual community, and as well we would like to build up a platform for knowledge exchange and bring together the knowledge of the research institutions to the industries, to the actual companies, so that we can bring up more pilots, more projects of these key technologies of quantum technologies here in Austria, and to support everyone in this community. But I would say enough from us now. I'm going as well to post my email address into the chat. I think, so if you want to, you're welcome to do so as well. So if anybody of the audiences are interested in just getting in contact with us, sharing your insights, you're welcome to do so. And just another information for this workshop. So we are collecting your questions, like in the bottom of your screen, there should be a question mark where you can describe or write into your questions you have for our speakers. You can do so during the whole session, and after both presentations, we will discuss everything, and then your question will be answered. So no worries. I think we will manage it depending on the time that every question will be answered. All right. In the meanwhile, I will share my email address as well. But first of all, I would like to hand over now to our first speaker, Dinka from the Austrian Institute of Technology.
Hello. So I will be sharing my screen now. Just to start the slideshow. Just a minute. Okay. Okay, so I come from AIT, Austrian Institute of Technology, and I would like to present our current progress in Project Kitty. So this is a project that's funded by the FFG program Quantum Austria. And I'm the project manager for this project. So Kitty, it stands for Quantum Communication Chip Scale Co-integration for Zero Trust Data Center Security. And in a few minutes, I will explain what this actually entails. So it's an exploratory project, and AIT is the only project partner here. So it's really closer more maybe to initial research, but we are tailoring it for some industrial needs, such as security within the data centers. So the project goals are development of quantum random number generators, as well as some chips for quantum key distribution, namely continuous variable quantum key distribution. We are working mostly on, we are a hardware-based project, so we want to develop a new, more integrated hardware to help the existing quantum key distribution systems. So we are focusing on photonic integrated circuits. We want to develop receivers and transmitters for CVQKD, and we would like to use the silicon platform because it's very mature. It has very good prospects for mass market because it inherited a lot of things from electronics. And also something that's relatively novel and was not done before, fully monolithically integrated receiver. So we would have photonics and electronics on the same wafer, on the same chip, let's say. And of course, we would like to experimentally evaluate this for DCI application. So we will do it, of course, within our own laboratory, but we will try a bit to emulate, to have also some classical signal transmission nearby, to try to emulate the higher temperatures, and to see what are we getting from our performance. So what is the motivation? So why quantum key distribution? Well, mostly because our current securities are at risk due to advances of quantum computing. So we need to find, again, a solution in the quantum realm for this. And quantum key distribution are expected to enable this information theoretic secure communication over large-scale networks. So we can really generate a secure key that's proof for eavesdropping. So if there is an eavesdropper, this would be detected, and then the transmission can be stopped. And our main application, since we have chosen a continuous variable QKD, will be, for example, within the data centers, because there we are not dealing with such large distances. At the moment, a lot of attention is paid to the security in north-south direction within the data center. So this is, for example, between the two data centers. But this perimeter security, it's deemed in recent times that it's not enough. There is also a lot of traffic within the data center, so between the different racks. So this is the east-west security. And we will also want to secure this part of the network. And this is called then a zero trust model. So like no part of the network is considered inherently secure. And if we want to be within the data center, of course, we need to fit within the rack. We cannot have a bulky systems. We want to be as compact as possible with our QKD hardware. And for this, a denser integration is sought to enhance the trust within this system. And yeah, this is why we are really looking into the continuous variable QKD. For example, a more mature QKD flavor is discrete variable QKD, but it can be rather costly and bulky, mainly because of the receiver side, because it either requires single photon avalanche detectors or even superconducting nanowires that need cooling, or in case of SPADs, they suffer from relatively poor detection efficiency at telecom wavelengths, and you need very extensive filtering. And because of this receiver side, it's not that attractive for integration. Of course, there are new advancements, and this might change in future. But also there is an issue of the speed, and continuous variable can solve these issues. It has a much better roadmap with compatibility with existing telecom technology. So you can have a brownfield deployment. You can use existing single node fibers. You don't need specialized dark fibers, and very good overlap with integrated photonics. So, but it just needs a different specifications, because in classical communications, they're also using some of the very similar components, but at much higher bandwidths, because that's where the industry is going. Here again, receiver is the biggest challenge. And this cannot be addressed by quantum community, so it's more of an engineering problem. So for photonic engineers and electronics to be really low noise and low loss. So this is the primary challenge, to have an ultra low noise amplifier at the receiver side, transimpedance amplifier. So, and by scaling it down, we want to scale down the size, but also we are aiming to scale down the receiver's noise. And this is why we are also looking into this monolithical integration that can remove some of the critical bond wires and parasitics. And of course, if this has an added benefit, if we don't have this one critical bond wire for electromagnetic interference immunity, which is also very important in data centers where we have, high switching speed of the switchbox ASICs. So this is why it's sought. Some further challenges are that, yeah, we want to remove all elements that cannot be integrated. For example, polarization control can be quite tricky to integrate. We will also try that in this. We are trying that also in this project. But as an alternative, we are also looking into a digitized polarization control. So we are trying to offset all of the functions that can be offsetted to the digital domain regarding the post-processing and synchronization of some signals, phase recovery, that these are done really in the digital domain. And really the bulk, the main analog functions that they are integrated for the best performance. Some other challenges that are not that much tackled so far are, for example, to combine quantum and classical transmit and receive functionalities. And for this, you cannot use off-the-shelf components. You really need some specific integrated solutions with switchable, for example, gains and bandwidths. And the last but not the least is to really adhere to the requirements of inter-data center applications. So really to be small and to be robust against additional switching noises, and temperature fluctuations. Then maybe to give just a few words, what is exactly CVQKD, if not everyone is from this field. Maybe DVQKD, discrete variable, is more well known. And this one uses a single photon detectors, and we have then just a single output. We have discrete outputs, so SPAD, single photon avalanche diode, either or superconducting nanowire is either triggered or not, so 0, 1. However, in continuous QKD, so we have a continuum of values that we can measure, and information is transmitted by encoding the quadrature components of V coherent states. So we have highly attenuated coherent states, and we are measuring the quadratures of the electric field. So its projections, projection of its phase and amplitude. And yes, I said the measurement outcome is a continuous value. And this weak signal needs to be boosted in order to be measured. And this is why we have a local oscillator. So this is basically a laser. So everything is done in optical domain until the photodiodes that transfer it to the electrical domain. And now, depending on the type of the measurement, so are we measuring one quadrature at the time or both, we can distinguish between homodyne and heterodyne detection. So in heterodyne detection, we measure both quadratures, and in homodyne, we will measure just one at a time. So this depends what are our needs for secure key rates and how much we want to compromise on the complexity of a solution. And just to be clear, this distinction of quantum heterodyne and quantum homodyne, it's very different than when we are talking about heterodyne detection in a classical sense. So here, heterodyne in quantum sense, heterodyne and homodyne means just are we measuring I and Q or just one of them at the time? While in a classical sense, we are more talking about intradyne detection, meaning is our signal at the baseband? So is our local oscillator in wavelength matching our signal, or are we offsetted, like are we in some passband, which can have its advantages? That's called then a heterodyne detection. And of course, there are mixtures of these signals of, like in a classical sense, how we make a system, but we are still, we can have very similar receivers like in the homodyne quantum detection, but we can be able to measure both quadratures, and I will show that also in a few slides. And these critical components at the receiver side are called optical mixers, either a 90-degree hybrid or 180-degree hybrid, depending on what type of scheme we are using. Okay, just a second. So some features of CVQKD. So basically, it exploits the Heisenberg uncertainty principle. So we don't know this exact position of our quantum states. So we just have some probability where we can find it. And this projection in the axis are defined in shot noise units. And as well, our detector noise is defined in shot noise unit. This is not too important for this presentation, but just to have in mind if you sometimes see it advertised, oh, this detector in this system has excess noise of this and this shot noise unit, just to know the term. So, and to be secure, to have this inherent security, we really want to attenuate our signal quite a lot to the level where the states, if we have, like, for example, a QAM modulation, so these different states will have significant overlap, as we can see in this picture here in different colors. So it's not like in classical communication when you can see really 4 distinct dots. Here, everything is so attenuated that you just have a probability where each dot can be found. So the eavesdropper can distinguish correctly the states. And if it tries to measure the states and retransmit the data, it will leave its signature. And we are talking here about really very, very low signals. How low? Well, at the transmitter side, we will have, for example, 1 photon per symbol. This would be for example, minus 70 dBm at this symbol rate. And usually we are at 15 50 nanometer wavelength, because this is a standard telecom wavelength that's used for the lowest attenuation in single mode fibers. And at the receiver, due to some transmission losses and inherent receiver splitting losses, we are going down to 0.1 photon per symbol, so almost minus 80 dBm. So we are really, really, really low, and we need to be very careful in how we design our receivers. Next. So how does the whole system look like? So this was one of our previous work. So this was all done with fiber optics and commercial components. But just to give a glimpse of the complexity. For example, this is the transmitter side. We are using the optical IQ modulator. We are using one pilot tone. So this is not a quantum signal. This pilot tone is used later for synchronization and digital post-processing. So it's an auxiliary signal. And we, of course, we have our quantum signal. We are separating both them both in polarization and in frequency in order not to have some bleed through of one signal to another, because pilot is much stronger than the quantum, and it's completely different modulation. So pilot is just a simple sine tone. We have around 20 dBs in difference of the signal strength. And we are using the polarization beam splitters in order to really separate them well. Of course, we need the attenuator. Here in the quantum side, we have additional attenuator because the quantum signal needs to be much lower. And we also wanted to emulate the resilience toward the classical channels. So these are commercial strength grade, some classical communication channels. And we could achieve relatively high transmission lengths. So this was from 13 to 28 kilometers. At the receiver side, we don't need some extensive filtering because of the coherent detection. So just a simple add-drop filter. And our signal will be chosen and filtered with the help of coherent detection through the local oscillator laser, which will be tuned to our desired transmission frequency. And then we have the optical components, the 90-degree hybrid, and there we have balanced photodetectors with the transimpedance amplifier and post amplifiers. We are feeding this. This was done offline, this post-processing, but it can also be in a real system, but you just need a bit faster analog-to-digital converters, and the post-processing can be done, for example, on FPGA, and this is something that's also being done now at AIT, but not in this previous work. So then we need to have a phase recovery, resampling, and a lot of other things to really get the CV parameters and these constellations. So in the end, I think we could get around, from the secure key rate, after all the post-processing, we could get up to 50 megabits of secure key rate. And our receiver had a bandwidth of 250 megahertz, because this was a commercial receiver. And as we will see now at the solution that we are developing, we are aiming at 1 gigahertz or above with the integrated one. So that's the complexity. And for example, we would like this part to be integrated for the transmitter. And for the receiver, this part over here, we want to integrate on a single chip. Next slide. So what have we been developing so far? So from quantum random number generators, so we are focusing on vacuum noise measurements. And previously, we already had some solutions with purely commercial components, such as planar lightweight circuit used as optical mixer, and some dye-level componentry for photodiodes and transimpedance and low noise transimpedance amplifier. And we could get a very high clearance, and NIST tests have passed all the requirements. In Kitty, we would like, instead of this PLC chip and separate photodiodes, to have them on a single die using the silicon platform, but also the monolithical optoelectronic integration, as well as, for example, in CVQKD transmitter, we would like there to have some QRNG engine, because this is QRNG is also integral part for QKD. It's needed for modulation of the signals. So it would be very beneficial that it's already present at the transmitter side. For example, here we have developed this chip where we have a transmitter that can be used either as a classical IQ transmitter or for quantum purposes. We just need to adjust our power levels through variable optical attenuators and to use the different driving signals. And we also have balanced photodiodes that could be then wire bonded to ATIA and used as QRNG engine. So these chips have arrived and are now prepared for measurements. And on the receiver side, yes, so in a classical sense, intradyne and heterodyne receiver have been made. We are still expecting these chips. And here are the balanced photodetectors on each side. That will be wire bonded to a low noise TIA in order to really get the best performance. And these TIAs have around 1 gigahertz bandwidth. So compared to the bulk, we are talking about the fourfold improvement. And some functional changes in implementation on a system level. For example, we wanted to test integrated polarization control on silicon. This chip is currently being measured, and we will see what are the losses. Is there a payoff to really have it integrated on silicon, or maybe it's a better solution to have a digitized polarization, not control, but polarization recovery. But for this, we need a scheme with 180-degree hybrid. So this would be a dual polarization heterodyne coherent system in a classical sense, but we can measure both quadratures, although it is a 180-degree hybrid. And we already had some tests with this, with our die-level receiver that I showed on the slide before, with the PLC and chip-level TIA. And we will try this also on our newly developed receivers. So this was purely photonic. This receiver and transmitter were purely photonic circuits that we are going to wire bond to our electronics that we have in a die form for best performance. And these electronics can be also commercially purchased, while the photonics is really a custom design, and they are not yet, as far as I know, readily purchasable solutions, at least not for quantum applications. There are some for datacom, but they're not suitable because of the footprint and how the photo detection is being done. It's not really a balanced photo detection, it's more a single-ended one, and that's not suitable for quantum applications. So from photonic side, we really need a custom solution. I have skipped the slide, I'm sorry. And lastly, we are also developing this fully monolithic approach, where we have photonics and electronics on the same chip. So it can be 180-degree hybrid. This is what we were focusing on, to have just a very simple design that we can use for CVQKD or QRNG. But also in future, it will be also a 90-degree hybrid for intradyne coherent detection, for sure. And current simulation results show that we can expect a 70% lower noise at the receiver side. This lowering of detection noise can directly be translated into the higher secure key rates and or bigger transmission distances. And we can also have some additional functionalities when we have photonic or this optoelectronic integration, such as use of Mach-Zehnder modulators. There's variable attenuators, or really a variable optical attenuator components, to really precisely balance the photodiodes. And then the common mode rejection ratio of the circuits, it's much improved, and this also lowers the overall noise. And here I have made a little bit to paint a picture of what are possible solutions and how the level of integration really impacts the receiver performance. So for example, some discrete solutions that are usually used in these off-the-shelf components. So we have TOCAN devices and fully packaged SMD electronic components. They really bring a lot of parasitics. And more parasitics doesn't mean just a lower bandwidth, but unfortunately also a higher noise. And the trade-off between the two becomes much more steep. So we're talking here about picofarads, but then if we look like what we had in one of the previous slides with the PLC, so just to come back shortly on this slide. So this PLC and TIA wire bonded to photodiodes. If we look at that, we are already much lower. So now we are in femtofarads and we have just a small bond wire that basically doesn't have that much capacitance. It's more inductance. That can negatively impact the electromagnetic interference, but it can actually even boost a bit the bandwidth. So it's not that bad. And these are also solutions with photonic circuits where we also need to wire bond to TIA. We just get even less parasitics because these photodiodes are waveguide coupled, not vertically coupled as with this pin chip. So we get even less parasitics, meaning better performance. And lastly, this is something novel that we are trying, really to have a monolithic or 3D integration. So 3D integration is more technologically heavy because you need two wafers and you need to interconnect them. So we opted for monolithic because there we had access to MPW and we can get relatively cheap prototypes for academia. And you can see that now the total capacitances are drastically reduced, and this can really, really have a big impact on the overall performance. So as I said, 70%, yes?
I'd like just come to and sum up then slowly your presentation.
Yes, just two more slides, I'm sorry. So we can have 70% lower input referred noise. We have made 3 variation of designs in the BiCMOS technology. We have also then, because it's a custom design, we can have a switchable receiver for classical and quantum communication. And here is some chart from one paper, how much the receiver noise impacts the total excess noise at the receiver. So it can be up to, so this was a typo, this is 60% of the total noise. So this is a really sweet spot for optimization. Another solution would, for example, for precise balancing would be not to use it on the photonic side, but in the electronic side. But this was not put to production because of a short project span and limited resources. But this can be also an interesting solution to reduce the losses on the photonic side and move some complexity to electronics. So next steps would be more system modeling and some simulation of alternative designs that we didn't have at the moment resources to make. And of course, laboratory characterization of the coming chips. Big challenges that can be expected when dealing with hardware miniaturizations are long wait times for chip fabrication, especially in photonics. It's not as mature as electronic technologies. And for us as academia, optical coupling, because there are not many service providers to really package your solutions. So we need to do all the measurements on our wafer prober. But if you're an industry player, that's not that big of an issue. Then all of them are working at higher volumes. So that's some maybe a conclusion to have in mind. But yeah, in general, CVQKD is recommended if you need higher CQ key rates than what's possible with DVQKD, but we are at the limited transmission span. So I hope that this was interesting for you. And I don't know what are your requirements of your businesses and systems, but this is more from a hardware perspective to tell you like where the community is going and what are the goals. And now there are some also initiatives that are aiming to improve a bit the services of PIC Technologies to really tailor them for quantum needs, such as QSMP initiative and QPilot, where they will have really processes and already like ready-made modules for chip integration for quantum communication, computing, and other quantum pillars. And that would be all from me. Thank you. And I will stop sharing now.
Thank you very much for your insights in your into your quantum project. And now I'd like to hand over to Manuel, who will give you some business insights, how they used quantum technologies at the Erste.
Thanks a lot. I mean, hi from my side. I'm Manuel. I'm a data scientist working at Erste Digital, which is the IT provider of Erste Group. And I mean, I will give you now more, let's say, an overview of how, I mean, what we're doing, but also what challenges, you know, there are of integrating or adapting quantum technologies in the industry, in this case, the banking industry. But just that we know what we're speaking about. This is just an overview where Erste Group is operating. Like I said, I'm working here at Erste Digital, and I'm an IT guy. This I want to say. Yes, let's jump into it. Basically, at Erste we have basically two streams when it comes to quantum technology. So we see there's on one side, you know, the benefits that the quantum technology can bring us, right? You can like things how to improve our banking operations. But on the other side, you also have the threat scenario, right? How actors could use quantum computers to harm us, right? Or to steal our customer data. And it started out, actually, our journey started out with the benefit side, but we soon realized that the threats are even, at least in the short term, let's say more important, because quantum computers can basically crack these most common encryption in the internet, the RSA encryption. And we're having use cases there on this side, also QKD, but I'm not supposed to talk too much about this. I actually don't know too much about it because I am on the benefit side. And basically, just to give you an overview, we have 3 use cases that we have been developing in Erste Group. 2 of them are quite easily to explain. One is a bit more challenging, but I'll go from the bottom, which is, you see, I mean, this is the 3 use cases: Earthquake, Quest, and Mosaic. Like, we spend a lot of time to find good names, but they actually mean something. Mosaic is basically Monte Carlo simulation that we implemented on a quantum computer, basically. Like, Monte Carlo simulations are one of the most common things done in banks, right, for risk assessment, and they're quite computationally heavy, right? Because I mean, what you basically want to do is to simulate, for example, things like the interest rates or asset prices or stock prices, right? And since there is always a component of randomness in every simulation, you want to do this thousands of times, 10,000s of times. And this is quite computationally heavy. And so a good use case for quantum. And we came up with a solution to do this on a quantum computer, and we want to patent this as well. And this is called Mosaic. This is one of the use cases. This is a prototype, not yet in production, but yeah, we'll come there. The next use case that we have is Quest. This is more my, let's say, area as a data scientist. It's for feature selection for machine learning models. You might know, in machine learning, one of the major components of a model is the features, right? And a feature could be, for example, if you want to predict if customers default on their loans, then features could be, their monthly income, or if a customer defaulted in the past, right? And we have in the bank machine learning models for fraud prevention and for product recommendation that have thousands of these features, right? We speak about 3,000, 4,000 features because they can be computationally created. And not every feature is a good feature. Not every feature predicts well what it should predict. For example, think about our default credit default example. For example, you could have a feature called zodiac sign, which is not very predictive, but in real life, it's not so easy to know which feature is a good one. And this is also computationally heavy to decide, from 4,000 features, what is fitting. So we also implemented this in Quantum, and we call it Quest. And this is available now throughout the bank, so people can use it. It runs both on a quantum computer and classically on your classical machine. This is most often the cheaper solution. And the third one, Earthquake. This is a really cool project. It's about customer screening. It's about actually CO2 screening, CO2 customer screening. You know, as a bank, we lend out money, and here we're talking about corporate customers that have lots of loans with us. And you know it from, if you take a mortgage, you normally have to pose a collateral, right? That has the same value as the loan, for example, your house, right? And when corporate customers, they have lots of real estate that they can, give us as a collateral for a loan. And what Earthquake does is to check, to optimize these collaterals that we take in for the CO2 emission. This is a new regulatory requirement that in a bank, or that we banks need to check how much CO2 we take in from the collaterals of the customers. And we simply thought we do this in Quantum. We had just a code lying around and tried it out, and it works quite nicely. It's also already in production, but also mostly classically executed, because Quantum hardware is still quite expensive. But yeah, I mean, this is not everything what we're doing. We do basically 5 things or 5 activities that we're trying to achieve. I mean, we're doing the use cases first. We're also doing patenting. We're trying, like I said, with this Monte Carlo simulation. We also participate in grants and competitions. We are in international conferences, and we collaborate with other banks, Europe-wide and actually internationally, in startups and universities. And for example, we are having also a student from FH Technikum, I think, that is writing a master thesis on this feature selector, which is quite nice. And just to give you an overview of what we've been doing so far. I mean, we've started this whole journey in 2022, so quite a while. We started with 10 experts. Now we're 5. It's volatile. We have these 3 use cases and a bit more. In Erste Group, the whole thing was started because basically as an innovation activity. I'm from the innovation department here, and simply wanted to see, is quantum computing already on a level that we can use in the bank? And if not, then we wanted to build up basically the knowledge to basically handle it once it is there. And this we've been doing for the last 3 years. But there is so far no real quantum department. So every one of these 5 experts that I wrote here have basically other different jobs, normal jobs. I normally say I'm in real life I'm a data scientist, but part-time I'm also a quantum scientist. And well, we have also some next use cases that we're looking into. I mean, here's a lot of names, I just want to impress, but in reality, we're looking into quantum machine learning. This is also something that's already, that is already possible. It's quite amazing how, when you look on the benefit side, that there are already Python packages like Qiskit that really makes it easy to use quantum computer, also if you're not basically really a quantum physicist. And this shows basically the maturity where quantum computing is already. Yeah, and then we have some business cases, default simulation, and so forth. But yeah, so it's going on. This is the message, and there's a lot of things that we want to investigate. Yeah, there's some, just to go through them. Basically, this is already it, what I wanted to show. So if you still have some questions, if there's more, I mean, we have some international and national cooperations with Spanish bank, with the IT provider of T-Systems. We're in some joint public-private initiative where we want to try to advise the government, like the Austrian government, on quantum technology. And quantum computing for us is a bit more than just the technical things. We have workshops together. We have quantum beer every Thursday. If you would like to join, just send me an email. And we won some internal prize from Erste Digital. And we have speakers in a lot of conferences. So that's it. I hope you liked it. I hope I gave you a bit of flavor what we're doing. And again, thanks a lot. Bye. for having me.
Thank you very much, Manuel, and thank you very much, Dinka. It was very fascinating insights. And from the webinar host, we've received the information that we have got some more time left so that we can answer as well some questions we've received. I think the first one was mentioned during your presentation, Dinka. It was about, are there any projects around photonic quantum computing like Xanadu's Aurora that are worth mentioning in this context of your presentation? You're still muted.
At AIT, we are mostly doing quantum communication. But for example, I know from my PhD mentor that they just had some project, I think it's called Epicus, where they were working on something for quantum computing. But for example, for quantum communication, it makes sense to have photonics and electronics on the same wafer. But it should be kept in mind that that's not always the advantage, because photonics is much larger. And then for quantum computing, you would have a very large photonic chip, like many Mach-Zehnder modulators that need to be tightly controlled. And if you want to route the electronics through that whole chip, that would not very be possible, and there will be a huge heat dissipation. So there, it was more advantageous to have like these heterogeneous integrations with wire bonding and have really specialized chips. But there is a completely different chip. These are chips for controlling. But this was a very interesting project. I think it was in silicon nitride that I heard of. And it was with European players, but I don't know exactly the names. So there are definitely some advances there. And I think industry is looking a bit more into quantum computing now than in quantum communication. I think they're looking, I know for some bigger companies that they are now having some interest in that, like Infineon, I think it's looking in that, like in Austria, and I don't know, some other. Yeah.
Okay, very interesting. So companies are interested in those new key technologies. And speaking about hardware, there was another question. I'd like this hand over to you, Manuel. Was like, how much are these technologies usable for, let's say, the real world applications? What quantum hardware do you use? I don't know whether you can say that. Annealing or gate-based?
Yes. So we're using gate-based. I mean, we were Erste was partner of IBM for some time. Now we changed to AWS out of management reasons, but it's basically AWS, is a marketplace for different quantum computers, and there we use Rigetti, also gate-based, and other companies. I think QEra is there. I have not looked into it, I have to say, but yeah, gate-based. And real-world applications, yeah, that's a tough question. I mean, we try now to do appetizers. I mean, this quantum feature selector runs also on the classical computer and can performs as well as classical feature selector that you use now in Scikit, for example. And yeah, that's the thing. We have always this we can use our applications both on a quantum hardware and both classically, so we call them quantum inspired. But yes, with the quantum hardware, it's still quite a jump, I would say, to make really something real world, to make it to apply the real world. But the thread scenario, QKD, PQC, post-quantum cryptography, is already way closer, and there our cybersecurity department already basically hired someone who is just doing this.
Okay.
I hope this answered the question.
I hope so too. To the audiences, if you still have some more questions, feel free to put it into the chat. Yeah, okay, just received the message that answered his question. But I have as well another question, because maybe this question is for both of you. So what I've heard as well, that there's like a big gap or between research and the use cases for industries. And maybe this question is very interesting for Sophie and for myself. What in your opinion, what Tinka and Manuel, what political, economical, or infrastructural changes are needed to accelerate those adaptations in quantum technologies to the industry?
Maybe I can start. I mean, I just know from other countries that there exist some things like consortia where the industry basically pulls together their resources and make basically the quantum hardware more accessible. I would also say that that would, you know, be a good signal to our management that, you know, quantum computing is being taken seriously already in the industry. So far, we have a bit of we fought basically for our existence, but it's it's going the right way, I would say. Maybe more, maybe also from the government, some hints could be interesting.
Okay, interesting. Tinka?
Yeah, well, in Austria, for example, there are not that many, I don't know, hardware startups for quantum. I know in some other countries there are, like Germany, Spain, Netherlands. So this makes it sometimes also harder because when you're academia or RTO, you always need to have some cooperation. So this is one part. I'm not sure how is the startup scene in Austria. On the European level, like there are now some initiatives like QSNP and QPilot that are moving forward. But, you know, these are really big consortiums. There are some advancements, but I think it just takes a lot of time, especially with these integrated solutions. I think also when like the main providers of technology, they are still academia. So then things might move a bit slower. In academia, usually we have also a high turnover of people because people finish their PhD, they leave. So I feel like they also need there's some lack of talent there, especially for some highly specialized fields like photonics and electronics. But yeah, there are now some moves, slow, but maybe that's to be expected. And also a little bit bridging the gap between people like who are doing the design of hardware and also knowing some things on the system level. I feel like there is some link still needed that there should be maybe a better communication. I think someone who is really like a bit more into the details of design, but also know from a system level very well what works, what not. I think a lot of times this is lost. Okay. So in these consortiums, like for example, when AIT is there, then usually there should be some expert from quantum side that has worked on systems, but it takes them a while to adjust to the terminology of really these highly specialized fields. And there has been a talk that maybe there should be master programs where they're really combining, for example, photonic design and quantum that people get like from both worlds, like quantum photonic designers and stuff like that. So I think there is a shift there now. There has been a lot of talk about this, how to educate the new generation. But yeah, it will take a bit of time.
Okay, thank you very much. Sophie, do you have a question left? The last one.
To be honest, I think these were really nice finishing words. I think there's a lot to do. It was really lovely to hear that there are practical applications of quantum technologies already. Also, Manuel, to be honest, I'm quite pleased to hear that the Erste Bank doesn't only look at the danger that quantum technologies might threaten them with, but also looks at the opportunities. So really good to have a positive outside. But if there are any last words from you, Tinka and Manuel, I can only say thank you very much from my end.
Thank you for having me.
Thanks as well, and see you next time.
Yes, absolutely. We'll stay in touch. The quantum ecosystem is only just starting out. As we've heard, there's a lot to do. But there's a lot already happening as well. So let's bridge the valley of death together and see that these pilots actually take off and we can do interesting new research and applications in Austria.
Thank you very much as well from my side. And I'm very already very interested how this community will change and take the next steps into the future. Right. And I would say thank you very much to all of our audiences. I hope you enjoyed this webinar as much as I do. I got very much new insights and could learn a lot. Yes, and so I wish you a pleasant day. Thank you very much for joining.
Thanks, everyone.
Bye.
Bye.